So, exercise 11. Today we will talk about a rather abstract topic, but I hope to give you some ideas that are behind it. The exercise we want to talk about stems from the chapter 7, which talks about deconvolution. Deconvolution means we have an operation, the convolution f convolved with u gives us something new that is called v, and deconvolution means we only know v and f, and we want to get u back. So it's like taking an inverse. And not only convolution, but a lot of operations that we know from mathematics and the applications have the following form that may remind you of a linear system of equations that you know from your basic courses in linear algebra, namely systems of the type ax equals b. So in our case, a is an operator, x is something that we apply this operator to, and b is the right-hand side. And if a is a matrix, then you know, okay, there are algorithms to solve this problem. Given b and a, we can also get x. Now, in functional analysis, these operators are sometimes integral operators or convolution operators, as we have seen in the course. And in the end, the type of operator does not matter. As long as it's a linear operator, we always get the system of the form ax equals b. And whenever we have a system of this form, the question is there a solution? So can we solve this system? Can we get x given b and a? Taking a closer look at this problem, it's not that simple because the solution itself may not be satisfactory. This is where the term well-posedness comes into play. And well-posedness is a new term talking about solvability of problems that consists of 3 parts. So the first one is, I think, the most natural one, coming from a linear system that we want to solve. If we want to solve it, the first thing that we need is that the solution exists. If we cannot look for something that is not there, we cannot solve a problem that does not have a solution. So even though we do not know the solution, it is still important to know that there is one. Yeah. So thinking about linear algebra, this means that b is in the range of a. Yeah, so this is something like a surjectivity condition on our operator a. So if we have a solution, it may also be a good thing if the solution is unique, meaning there are no 2 solutions. If I have a solution, I have the unique one. If someone else finds a solution to this problem, maybe with a different method, it is still the same solution. So talking about linear operators, these 2 together are some sort of the trivial parts or the basic parts that we need for writing down something like a to the minus 1. So the inverse. A to the minus 1 applied to ax just gives me x. So if I apply it to ax with equals b, I can get the solution x from the data b. So now the third part is what makes this term of well-posedness something more suitable for solving problems like deconvolution or partial differential equations that we also have been looking at. And this third part tells us we want continuous dependence of the solution on the data. So what does this mean? So in practice, all calculations that we do, they come with errors, or they have errors. And I'm sure in your numerics class you have learned about the possible errors that can occur with a model. So we can have modeling parameters that induce errors, like discretization, or just a model that is not exact. The second part that we can have are just due to the fact that we may solve things with a computer, so we may have floating point precision problems. And these errors, of course, they reflect maybe on A or on the right-hand side B, and they change our system. And therefore, they will also change the solution. But if we have continuous dependence on the solution, of the solution on the data, this means a small change in the data. So let me phrase this like this. So small input errors, they still lead to, in some sense, controllable errors in the result. Even more, the continuous dependence tells us when the error of my input gets smaller, then also the error of my output will get smaller. So this is something that we would expect of a good algorithm that solves a problem. So now we want to see how this well-posedness is related to a property of linear operators, which is compactness. And to this end, I brought a very simple example that may not be a realistic one, but it's so simple that we can observe everything that can go wrong with inverting an operator and looking at the continuous dependence on the data of a problem AX equals B. And this is what I brought in exercise 7.3D. Yeah, so I think it's better if I just share my notes with you. Okay. So in this operator, what we see, first need to share my notes, sorry. So the operator that we want to work with is an operator that works on a space of sequences. So this, let us call this operator A, and it maps a sequence. I denote the space of sequences here with L0 to L0. So given a sequence, so an infinite sequence, you may recall from one of our first chapters, we can also think of them as infinite vectors. And the operator that we want to look at maps this infinite sequence to a new infinite sequence. But now the first term is multiplied by 1. The second term is multiplied by 1/2. The third term is multiplied by 1/3, and so on. Yeah, so as an example, if I have a constant sequence, the sequence that only consists of ones, then A maps this constant sequence to a sequence 1, 1/2, 1/3, 1/4. So this would not be a good example if we could not visualize what is going on here in a very nice way. And an operator of this type we can see as a semi-infinite matrix. And it's not only a matrix, it's a diagonal matrix. So what do I mean with that? So matrices, we know them. And so let me just start with a bracket here. And on the diagonal, I just put the multipliers 1, 1/2, 1/3. And so on, yeah? So 1/4, 1/5, and so on. And all the rest of this matrix is 0. So infinite means I continue these zeros and also this diagonal, which is just a sequence 1/k, infinitely long, yeah? So now I'm not in the finite dimensional vector space, but an infinite dimensional one. So the objects that I apply this infinite matrix on are infinite vectors. Yeah, I just wrote them here. Now I wrote them as transposed vectors. So x1, x2, x3, and so on. And now with the basic rules of linear algebra and matrix multiplication, we can also make sense of this product of an infinite dimensional matrix with an infinite dimensional vector. Yeah, just as we would do with usual matrices. We take the first row and multiply it with the vector. And as it only contains one non-zero element, the result here is just 1 times x1. Same goes for the second row. I have 1/2 times x2, 1/3 times x3. So this should be an x1 here. And so on. So this is the mechanics of how this operator works. And we want to consider this operator now on a subspace of sequences that you also know well from one of our first chapters, which is the subspace L2. So the restriction that I want to consider now is the restriction A2. So I have a little subindex 2 here that tells us I now want to apply this vector only to elements of L2 of n. And of course, I also want to get out an element of L2 of n. And this is something that we need to prove in the first part of this exercise, so that this is really a well-defined operator. I have seen here I can apply it to a sequence and I get a sequence out again. And now the question is, if I apply it to a sequence that is in L2, do I get out an L2 sequence again? Short recap, what is the space L2? So L2 of n is the space of all sequences. Let us denote the sequences by like an infinite tuple that is indexed over the natural numbers. And so the additional condition on elements of this space is that the 2 norm is finite. So what do we do in this case? We take the sum going from k equals 1 to infinity of the norm of the element squared, and this should be finite. Sometimes we also denote this by 2 bars. Then we write the sequence in here. So this is the 2 norm squared because I left out the square root. And if this is finite, so strictly smaller than infinity, then I have a sequence that is in L2. And if I start with a sequence in this space, now A2 should also map to something like this. And this is what we call well-definedness. Sorry, well-posedness is something else that we will look at this in this problem here. The first step is to see that A is actually a well-defined operator. This is part A. Okay. So I think I already outlined how the proof is going to work. So we start with x, and vector, infinite vector, in L2 of n. So this means, so we should keep this in the back of our head. This means the 2 norm of x is smaller than infinity by definition. So now I want to show that also the 2 norm of the image, so A2 of x, is also finite. So how do we do this? We just plug in the definition. So the 2 norm squared, so this gives me a sum from k equals 1 to infinity. And as you may already guess from this matrix definition here, So the nth component of a2x is nothing else than 1 over n times xn. Yeah, so the first gets mapped to 1 times the sequence member. The second gets mapped to 1 over 2 times the second sequence member. And now if I take the 2 norm, I need to go through all k from 1 to infinity, which gives me 1 over k times xk squared. This is just the 2 norm of a2 applied to x. So how can I now estimate that this is smaller than infinity? A little trick that we can use here is that 1 over k, this is always a number that is less or equal than 1. So I can also estimate the whole sum by using the sum from k equals 1 to infinity of xk squared. So, but this here, this is nothing else than the 2 norm of x squared, which is smaller than infinity by definition of the L2 space. Yeah. So in conclusion, a2x is also an element of L2 of n. And a2 is well defined. So we start out with an element x in L2, and we get out that a2x is also in L2. So the second part of the exercise now wants to show us, and in this part we want to show that a2 is bounded and compact. So bounded also means continuous in this setting. This means if x changes, then also ax will change in a controllable way. So what do I mean with controllable? So bounded is the same as continuous in our case. And this means I want to show that a to x in the 2 norm is smaller than a constant times x in the 2 norm. Yeah, and you see already, in order to write down something like this, we need the well-posedness. So a2x needs to be in L2, so I can write down the L2 norm here. So let me give this equation here, or this inequality, a star, and show, let us see if we can find a constant c such that I have this controllability of a2x by x. So if we take a closer look at what we did in part A, we see, let me mark this with maybe with red, we see that the 2 norm of a to x is less or equal than, well, this sum here, which is the 2 norm of x squared. So this means we can just write a to x in the 2 norm smaller than x in the 2 norm. So this inequality star holds with the constant c equals 1. Yeah, and a2 is a bounded operator. So the next thing, so bounded, we can mark with a check. The next thing we show is that a2 is compact. And what can you think about if you want to know what does it mean for an operator to be compact? There are a lot of different notions. Some of them you have seen already in the lecture. And the notion that we want to work here with is also, I think, a practical one from the point of numerics, which I will write down here. And it's a notion of approximability of an operator. So A2 compact means that A2 can be approximated uniformly by operators of finite rank. Yeah, so this question of approximability here comes into play, and if you are interested in more thorough coverage of this topic, you can visit next term the lecture of Marco Lindner on approximation and stability. What we do here is very elementary. Let us take a look again at this matrix here we have on the left-hand side. So an infinite matrix, it also has infinite rank. Yeah, so the image of this matrix will also be infinite dimensional. But what happens if we consider so-called finite sections of this matrix? What do I mean with that? Let me just use this here again as a blueprint. So one natural way to approximate such an infinite matrix would be by taking just a finite submatrix and zeroing out the rest of it. Yeah, so I just take this red square and then set 0 to the end. And this one I would call A2. This upper left corner I could call A1, or maybe let me use a different notation. So this should be A1, this should be A2. And for the third one, let us take this third submatrix, A to the 3, and always zeroing it out, so we have still an infinite matrix, but now with a finite rank, because I only have a finite portion of this matrix that is non-zero. So how can we now show that this really approximates our matrix uniformly, our original matrix A2? So let me first note that AK has a finite rank. And now we show that AK converges to A2 in the operator norm. So I will explain this term to those of you who are unsecure what this means in a second. I first start with the calculation where all the terms that we need come up. So we take a look at the difference. So approximating always means taking a look at the norm of a difference and showing that it goes to 0. So we start out with the difference of A2 and A2 to the k. So this is our kth submatrix, and we apply it to a vector x, and we look at the 2 norm of it. Then we see that this is smaller or equal than the norm of, so where do I start? Okay, with n going from k plus 1 to infinity, 1 over n squared times xn squared. So how does this, so what is happening here? So think about the matrix on the left-hand side, and I just subtract. So the subtraction is seen here, this part from the left-hand side. Then the upper left corner up to the kth diagonal will be zeroed out, and the rest of this diagonal that we find here will still remain, and therefore this sum starts at k plus 1. All right. Can we simplify this more? We can. So we can estimate this by the sum going from n k plus 1 to infinity, 1 over n squared times the 2 norm of x squared. So how does this help us for the operator norm? So the operator norm is like a norm for vectors, but now for linear operators, therefore the name. So this norm only takes operators, and in our case it takes the difference of the operators A2 minus A2 to the k. So the definition of this operator norm is that we take the supremum of all vectors x2, x in L2 with norm 1 and look at the norm of the image. Now of this difference here, so I have a2 minus a2 k of x squared. So, and as I already saw, or as I can already see from the inequality here, if the norm of x equals 1, so let me mark this maybe in pink here. So if the norm of x equals 1, then also this guy here will equal 1, and we can estimate the supremum, as we can estimate each element that we consider the supremum for, by the sum from n equals k plus 1 to infinity of 1 over k squared. 1 over n squared, sorry. So, and as you know from the fact that a converging series needs to have how do I tell? So, as a fact for converging series, we know that the series of the rest, or the sequence of the rest that I consider. So the rest of the series is always starting from a particular point and summing up all the remaining parts of the series, needs to go to 0 if n goes to infinity. So, but if this part goes to 0, maybe let's mark this in orange. So if the right-hand side goes to 0 for n going to infinity, then also a2 approximates a2k, or these finite sections approximate a2 in the operator norm, meaning uniform approximation. So, so to sum up, or in conclusion, a can be approximated by operators of finite rank. And by definition, or by a notion of compactness, this means A2 is compact. So compact and bounded. And now we want to come back to the notion of well-posedness. So this means we not only wanted to, we now want to consider the inverse of our operator. So these are the three things: existence of a solution, uniqueness of a solution, and continuous dependence of the solution on the data. Let us first take a look at the inverse of A2. So if I have a diagonal matrix, calculating the inverse is straightforward. So how should the inverse look like in terms of an infinite matrix? Well, we just take the reciprocal value of the elements on the diagonal. So the inverse of A2, so let's say A2 to the minus 1, should be something like the following matrix: 1, 2, 3, and so on the diagonal, and zeros everywhere else. Still a semi-infinite matrix. And as we see, the diagonal has been changed to the reciprocal value here. So instead of multiplying with reciprocals of n, I now multiply with n. So the first one gets multiplied with 1, the second one gets multiplied with 2, the third one with 3. Yeah, so if I take a semi-infinite vector here, the result is x1, 2x2, 3x3, and so on. And now we can go through the parts that we just covered for A2, but now for the inverse. So first of all, the inverse cannot be defined on the whole space L2 of n. Yeah, you can think of this multiplication as something very severe. If the multiplication does not decay, then our operator will not map an L2 sequence to another L2 sequence. Therefore, we have a little technical detail, which is a domain of definition. So we can only apply A2 to elements of D of A2 to the minus 1, which is, I just write it down briefly, are all the sequences xn in L2 of n, such that A2 minus 1 of xn, or I do not need the 2 here. So A to the minus 1 of xn is an element of L2n again. So this is just a technical point. We do not need to get into detail here. The important part is you see that it is easy to write down what the inverse needs to look like given an operator that has this diagonal structure here on the left. That's precisely the one on the right-hand side. And if I take elements out of D of A2 minus 1, then I also know how to calculate the inverse. I just multiply the elements with 2. So after this technical detour, what have we seen so far? So A to the minus 1 is an inverse. It looks good. Yeah. So in terms of matrices, if I have a linear system and I can calculate the inverse matrix, I can also determine the solution by just calculating A to the minus 1 2p. Gives me the solution. So this means in some sense we have already cleared that for our well-posedness question, existence and uniqueness are guaranteed. Yes, we may need to restrict the set of values that we allow for B, yeah, to the domain of definition of A to the minus 1. But if we do that, then for these right-hand sides B, we can always guarantee that there is a unique solution. But does the solution also depend continuously on the data? So the question in part D, so the final question that we want to ask is, is A minus 1, 2 continuous? And we now show that it's not the case. It's not continuous. So the problem is not well posed. So this is the part of the problem that we now want to look at. So given a constant C, we need to find an element of L2 that is bounded. It's just bounded by 1, but that the norm of the image is greater than C. So maybe it makes more sense to think about this question posed with a B here, yeah, in terms of right-hand sides. So for every constant that you can think of, so let's say C is 1 million, then I find a right-hand side that is in the norm smaller than 1, such that the solution corresponding to this small input is larger than 1 million. And I can also I can change 1 million to 1 billion or 1 trillion, and it will always tell you, well, I start with something small, a small right-hand side. The norm is always less than 1, but the outcome grows, just as I like it. So let me write down once again the definition of A2 minus 1x of n. So this is just nothing else than n times the nth term of our sequence n. So what does this mean for the 2 norm? We always need to consider 2 norms here. So the 2 norm is nothing else than k squared times xk squared. So how do we now find, so this holds for all x in the domain of definition. How do we find the b like this? So we choose an n such that the sum from 1 to n of k, so I just sum up the first n natural numbers, and I know, well, if I sum them up, I will surpass a given c. And now we define our sequence also via a cutoff. So it should be 1 over the square root of k if k is smaller or equal than n and 0 else. So it's a finite sequence, and it also has the property that the 2 norm of it, so the sum from k to n, 1 over k, less or equal than the sum from k, just summing up 1 over n times equals 1. Yeah, so the first part of this exercise is already fulfilled. But so what we care about is the second part. Is this really a bad sequence in the sense that the image of a to the minus 1 of it is really larger than c? And this is also a short calculation. So a to the minus 1 of the sequence x that I have defined here is the sum going from k equals 1 to n of k squared. This is just what I just calculated here. And xk, so 1 over the square root of k squared. So, and this is just the sum going from k1 to n, summing up the n first natural numbers. And by definition, or by construction, this is larger than c. So in conclusion, a to x equals to b is not well posed. Yeah, so this is something that won't happen in the finite dimensional setting. In the finite dimensional setting, you would just, what do you do with a matrix? Well, you look maybe at the determinant. The determinant is non-zero. You can solve the problem always. In this case here, even though we can invert our matrix in some sense, continuity of the inverse fails. And this is not something that is particular to the example that I choose, but to all compact operators. So this is the part of the exercise that I am not going into detail here because it's too advanced. But compactness of an operator already implies, so no calculations needed like this, to know the inverse won't be continuous. And here we have seen an example for an operator that is hopefully fairly simple, and we can just calculate through the discontinuity of this operator and see what it really means, how it looks like, and get maybe a first feeling of what this means for an operator to not have a continuous inverse. And we have seen these operators in the lecture, our convolution operators. They are also compact and bounded, and you have seen that the inverse, well, it's not well defined. Or even if you define it with means of Fourier transform methods and so on, there are always some technical details that are skipped due to the fact that the operator does not have a bounded inverse. So what does this mean for practical applications? In the practical applications, you will have very large matrices that have a very high condition number. So even though the matrices are still invertible, calculating the inverse by means of a computer is not recommended. So there is also another exercise that we won't be covering here, but you find it in the lecture notes that shows you how you could naively discretize a convolution operator and try to calculate its inverse by means of a singular value decomposition. And you will see that it works very bad. So it does not work at all because the condition numbers are so high that even though mathematically you can calculate an inverse, because it's just a finite matrix, numerically you won't get out anything that makes sense. All right, so that's it for today.